So linear algebra is the algebra of lines, unsurprisingly. So maybe we should start out by talking a little bit about lines, linear equations, and then we can talk about their algebra, right? So to begin with, what I'd like you to consider is suppose that we have two linear equations in R2. What are three different ways that the lines can interact in this space? So take a moment, pause the video if you need, to consider how two lines in R2 might interact. You got some ideas? All right, that was the top coming off the pen. So the easiest way, I guess, that two lines can interact is they cross, right? So we could have one line going this way, and then the other line going that way. So we have two lines interacting in this manner. They just cross at a point. The second way that two lines can interact is really like not to interact at all, right? So you could have two parallel lines. So we could envision two parallel lines here. Pretend those are perfectly parallel, if you will. And how about the third way? What's a third way that two lines can interact on a plane? Well, it's kind of weird. They would interact by being the same line. So a third way that two lines can interact is that they are secretly the same line. They were the same line all along. All right, cool. Let's look at another example. All right, so now that we have a graphical way of thinking about how lines might interact, let's compare that to an algebraic expression or algebraic equation for those lines, for those examples. So for instance, let's say I wanted to write two equations for lines that intersect. So really what I have to make sure here is that they just don't have the same slope, right? So if I were to write y equals 2x plus 3, that would be one equation, and then I could write, say, y equals negative x plus 4. I don't know. So those are examples of lines that would intersect. So if I don't want them to intersect, I've got to make sure they have the same slope. So that would be this situation here. So we could have like y equals 2x plus 3 again, and we could have y equals 2x. So these two lines have a different y-intercept, so they're not going to intersect there, and they have the same slope, so they're just going to run parallel to each other. And then for our third situation, we kind of want to build on sort of what I mentioned here. They have different y-intercepts, so they want to intersect. So now for the two lines to secretly be the same, we just need one to really be a multiple of the other, or a rearrangement of the other. So for instance, we could say y equals 2x plus 3. And then if we wanted to, we could have like 2y is 4x plus 6. Or we can move the 3 over and we get y minus 3 is 2x. It's literally infinitely many choices here. So this is just as a way of coming up with some examples that satisfy these particular conditions. All right, so we've got some examples set up of what these things might look like. So let's look at an example and see if we can figure out, for instance, where these two lines would be crossing, or where two lines that we're given will cross. All right, so here's our system that we're going to solve. We want to solve the system x plus 3y equals 1 and x minus 6y equals negative 14. So there are a few different ways that you can go about graphing these two equations, but what I noticed that I think is going to help me out is that both of them have a coefficient of 1 in front of the x. So I can solve for x for these two equations and then plot some points and graph that way. So figure some values for y, substitute that in, and that'll give me my x value. So yeah, let's do that. If I were to solve this equation for x, I'm going to subtract 3y from both sides. So I'm going to end up getting x is 1 minus 3y. And if I add 6y to both sides here, I'm going to get x is 6y minus a 14. Right. So yeah, so now we got to pick some points to graph. So because I'm a hand from the void reaching out to say hello. Okay, so sorry. So if I want to graph this line, I've got to pick values of y that are going to go along with my graphing space, right? So my graphing space that I've provided here goes from -2 to 4 along the y-axis. Now, usually, right, we're used to slope-intercept form being, or function form being the standard way we see lines. So we're accustomed to substituting in for x and then finding y. But again, just because it was easier here, we're going to sort of do the reverse. So I'm going to substitute in values from -2 up to 4 to try and get a few points that are going to work for us. So if I plug in, I don't have a lot of space here, so I can't write too much down, but if I substitute in, let's say -2, that's going to give me 1 minus 3 times -2. So 1 plus 6, which is 7. I don't have an x value of 7 over here, so not good. I do know if I plug in 0, that's going to work, right? Because 1 minus 0 is 0. So if y is 0, did I say 1 minus 0 is 0? My goodness. 1 minus 0 is 1. So we know that we're going to get the point 1, 0, and that we can graph. All right. Let's see. If I substitute in 2, we get 1 minus 6, which is -5. So if I substitute it in 2, I'm going to get 1 minus 6, which is -5. So I have the point -5, 2. Okay. And we could connect those 2 points here. I'm going to find one in the middle. So let's say I plug in 1. So 1 minus 3 is a -2. So I also get a -2 and a 1. So now I've got some points. Preferably use a straight edge to connect these. I'm not so capable of that at the moment. So I'm just going to do my very best. And I'm going to label this line 1 so that I know that was line 1. All right, so take a moment, try the same technique to graph the second line, and pause the video. And when you unpause, you will see how I have done it. Those are words that I am speaking. All right, see you in a moment. All right, so hopefully you've taken a moment to graph the second line. I switched to a different color, just use red to graph this line. So I'm calling it L2. And I found it by substituting in 1 and then 3. And those gave me 2 points that were super far apart. So I chose a number between because my y-axis was given in halves. I thought maybe 1.5 would work nice. I could have done 2, but why be boring, right? So I did 1.5, it got -5. And then this was the line that I drew. I graphed. There we go. Hopefully yours matches, right? Yay. So to solve the system graphically, we want to see where do these 2 lines intersect. So we've got this point of intersection here. And now if I had a straight edge, my lines would be much more accurate. If I had evenly spaced grid instead of freehandly drawn, my solution would be much more accurate as well, right? So this is going to be an approximation. And even if everything is drawn perfectly, it would be an approximation because these 2 lines don't intersect in a really nice point. So I'm just going to draw a line here to help me eyeball. Okay, so it looks like the x value where they intersect is going to be maybe 3.8. 3.8 seems, -3.8 seems like a somewhat okay solution or estimation there. And then the y value is just under 2, but remember our scale is different. So maybe this time it's a little bit closer to 2, so maybe 1.9. So this is going to be our approximate solution that we came to because of our graphing. If your graph is more precise or more sloppy than mine, you may get a very different solution. So I noticed, right, when I graphed this line, this was still too long. I should have picked another point in between. So it kind of got a little bit sloppy at the end. So that's going to change some of the direction of the line, little things like that. So one of the problems with solving a system of equations graphically is the inaccuracy of it, right? So there's so many different things that can interact with them. They could even intersect in like an irrational point. So you would never be able to guess that, right? So we want to find some other ways of solving these lines. But before we get there, you probably have seen how to solve systems of 2 equations and 2 unknowns in the past. You may have even seen 3 equations and 3 unknowns. But what if you had 5 equations and 20 variables? Or what if you had 20 equations with 3 variables? How would you even begin to go about attempting to solve such a thing, right? So I've got one more question to pose before we start moving into some algebraic techniques. All right, so now suppose instead of living in R2, we lived in R3, which is what most of us experience, right? We live in 3 dimensions. So how might 2 lines, still like a y equals mx plus b situation, so how might, well, or maybe y equals mz plus b, right? Because we're living in 3 dimensions, so now we have 3 variables. So how might those 2 lines interact? Are they going to interact in only the same ways that they interacted in R2? Or are they going to have some new possible ways of interacting? So this is a thing that I'd like you to sit on and ponder. I'm not going to answer it right away. I want you to kind of think about it and dwell on that as we jump into some really like formal definitions. So we've been talking about systems of linear equations. So let's talk about exactly what that means formally. And then we'll do some algebraic techniques for solving these beasts.